stress, strain, and elastic moduli, and this is our first example problem. A relaxed biceps muscles requires a force of 25 newtons for an elongation of 3.0 cm. Okay, so we've got here our force, which is here force 1 is equal to 25 newtons with our elongation of 3.0 cm. So that's basically the elongation, L, corresponding to our first force, so that would be delta L1, which is 3.0 cm. The same muscle under maximum tension requires a force of 500 newtons for the same elongation. So we've got the same muscle, but different condition. Force here is 500 newtons. And again, delta L2 is the same, 3.0 cm. Find the Young's modulus for the muscle tissue. Says, find the Young's modulus. So we're looking for this symbol, Young's modulus. For the tissue under each of these conditions, if the muscle is assumed to be a uniform cylinder with length 0.2 m and cross-sectional area 50.0 square centimeters. So if we are assuming that the length of our muscle is 0.2 m, then that must be your L0, your original, and the cross-sectional area is 50.0 square cm. So that's since we've already identified the given data, let's have a quick recap of definition. By definition, Young's modulus is basically, in terms of your force, by the way, is basically force all over area is equal to Young's modulus, your deformed system all over your original one. So change in L all over L0. And we're looking for Young's modulus. So we just need to transpose. That would just give us I shall divide it. And then that'll just give me F over A, because I'm dividing this by delta L over L0. That would just basically multiplying. That is L0 all over delta L. Okay. And trying to substitute our F1, basically, because this is the first one, F1, A1, everything's 1. Our F1 is 25.0 newtons all over my A1, which is basically 50 cm. But it's instead of having it cm all the time, I can actually convert it to m. So that will be 50.0 cm. Okay, with a conversion unit here, that is 1 m squared cm squared. Okay. All right, multiplied to my L0. L0 is 0.2. No need for any conversion there. All over my delta L. Delta L here is 3.0 cm. So from 3.0 cm, you can convert this 3.0 cm, not squared. Convert this 1 m 100 cm. So basically, in 1 meter, you've got 100 cm. So you can cancel this out. We use a different color to see which ones are cancelled. Cancel. So you've got m. This is, by the way, newtons. Cancel. Okay, so you're going to be left with Newton per meter squared. Right away. Oh, missed this one. Newton per meter squared. So if we just calculate this would just give us 3.33 times 10 to the 4th Newton meter squared. That is for Young's modulus number 1. For our Young's modulus number 2, it's the same thing, same procedure. You just have to try and change the given. Remember, you've got to convert what you need to convert. So I'll just put it here. This is my Young's modulus number 1. My Young's modulus number 2, everything would be in 2. I just need equals, my F2 is 500. I'll just leave the units behind. And at the end of the day, I've got to have Newton per meter squared, square meter. So 500 all over my area, which is 50. Again, 50 cm. Okay, I'm just gonna put the units here so that you know how to convert. So 50 square cm multiplied to, in 1 square meter, I've got 10 to the 4th square cm. It's the first one. Multiplied to my L naught. My L naught here is said to be 0.2 again, all over delta L is 3.0 cm. Again, 3.0 cm, which is basically in 1 m, I've got 100 cm. Okay. Then cancel each common terms. I've got m here, m, cm, cm. So we're going to be left with your Young's modulus number 2 is actually 6.67 times 10 to the 5th Newton per square meter. There you go. All right. It only means that the Young's modulus for the relaxed biceps muscle is lower than the one under maximum tension. Next one is again stress, strain, and elastic modular, but this time we're going to be talking about metal rod that is 4 m long and 0.5 square cm in area or cross-sectional area. It's found to stretch 0.20 cm under a tension of 5,000 newtons. What is Young's modulus for this metal? So we're going to be identifying the Young's modulus again. Let's identify the given first. According to this, metal rod that is 4 m long, so that will be our L naught. L naught is 400 m, and my area, cross-sectional area, is 0.50 square centimeters. Stretch 0.2, so that would be our delta L, 0.2 cm. Under a tension of our force is equal to 5,000 newtons. We're looking for the Young's modulus, which is denoted again as this one. A quick recap, our Young's modulus in terms of your force is just equal to force all over area. That is our common formula there. Is equal to your Young's modulus times deformed length all over original length. So we're looking for Young's modulus, we just need to transpose or divide everything by delta L all over L naught. The next is, see, if I need to be making use of my Young's modulus, that would just be my F all over my area times the denominator of this, L naught all over delta L. Okay. And substituting, my force would just be 5,000 newtons all over my area, which is, according to this, 0.50 square cm with a conversion unit. Again, just, oh, so sorry. Okay, I'll just plug it in right away, so it's not too long. Okay, so 5,000 newtons, okay, all over my 0.5 times 10 to negative 4, that will be at my square meter, times my L naught, which is 4, no conversion needed, all over my 0.20 times 10 negative 2m. And that would just give us 2.0 times 10 11th Pascal. If you remember, Pascal is also equal to Newton per square meter. So we can actually say 2.0 times 10 to 11th power Newton per square meter, or 2.0 times 10 11th pascals.